used to be a really big thing in the CCIE lab, but these days it is there. You need to know about it. You cannot probably pass the lab without knowing frame relay, but they're not going to be extremely detailed and they're not going to go very, very, very deep into it. But still, you need to know fundamentals. You need to know a thing or two to actually be able to do it correctly and do it the right way. So what am I going to do today is I'm going to use a very, very simple network to demonstrate the frame relay. So this is going to be the network that I am going to be using today. And also keep in mind that this is the network that you will be seeing many times throughout this week, because I don't believe that you need to have an extremely complicated network setup, an extremely complicated network design in order to demonstrate the behavior of protocols, to demonstrate the things that that you are working on. You need to have 3, 4, 5 devices at most to be able to explore the technologies in depth. So for the frame relay, I'm going to be using just these 3 devices. But because of the thing that I mentioned earlier, that in your lab, you are actually going to have one of your routers be the frame relay switch, what we are going to do here in our setup is we are going to configure R5 to be the frame relay switch. So we are going to be configuring the frame relay switch, and we are going to be configuring our R2 and R4 to be the endpoint devices. Before I can actually go in and talk about the endpoints, talk about the frame relay and explore this in detail, I need to clarify one thing that I have seen many of my students struggle with. And it's a very, very simple concept. It's the concept of DTE and DCE. Now, we all know that DTE stands for Data Termination Equipment, and that DCE stands for Data Communications Equipment. Now, the problem here is that there are 2 unrelated things, 2 unrelated concepts that use the same terminology, and frame relay is just one of them. Now, on a fundamental level, when we have 2 routers, let's say R1 connected to R2, and that are connected over the serial link, one of these routers needs to provide the clocking, needs to provide the speed. So the side that actually provides the speed on layer 1 will be the DCE. The side that receives the speed, that receives the clocking information from the link itself, will be a DTE. And this is on layer 1. Now, when we have a back-to-back connection like this, when we have a router that is directly connected to the router, the side that is DCE is determined by the kind of the cable that is plugged in. And it's a special side of the cable, special connector that is called the DCE connector. And you can actually see this if you type show controllers, serial interface. The interface will tell you, the router will tell you which side of the cable is actually plugged in here. And again, this is something to do with layer 1. Now, frame relay itself also uses the DCE-DTE terminology, and the frame relay switch on layer 2 is called the DCE device, while the endpoints are called DTEs. Now, it's important to understand that there is no relationship between this and this. These are 2 completely separate concepts. Now, the reason why I'm spending time talking about this is that I have seen students struggle with this idea when they would go into the lab and they would see, for example, that there is a requirement to configure R5 as the frame relay switch, yet this device here is the serial DC. And they would say, but this is impossible, this side is DC, how can I make it a frame relay DT? Well, you can, because they are completely unrelated, they do completely different things. So, as I said, in layer 1 DC, this is what happens. Now, when we talk about frame relay and when we talk about DCE-DT, they have a very, very different function. So let me talk about that just a little bit. So I'm going to do one thing here now. So again, I have this network here, and let's say that this is going to be our serial DC, and this is going to be our serial DC, which means that this side in both cases is the DT on these serial interfaces. But because this is a frame relay switch, on frame relay on layer 2, frame relay switch is going to be acting as DC in both cases, and these are going to be DTs. So for frame relay functionality, the function of DC is to respond to LMI inquiries by sending LMI status responses. Now, one thing to note about the DCE is that it will never ever, it never sends LMI inquiry. Now, the DTE side, on the other hand, and DTE, by the way, is default on Cisco routers, it will send LMI inquiries, and it will never send LMI status. Now, this is important because I mentioned that you might have situation in which you need to troubleshoot the frame relay switch in the troubleshooting section of your lab. And this is very, very important because you can end up in the situation where this is causing some communication not to work, and you need to know where to look for it. So what I'm going to do now is, again, let me just clone this page. So all these examples here, I'm keeping them. So I'm starting with the fresh page that just has this background here. So what I'm going to do now is just a very, very simple configuration. I'm going to bring these two interfaces up. I'm not going to configure any IP addresses, not going to configure frame relay to begin with. I'm just going to bring the interfaces up and make sure that I get CDP neighbors so to verify that interfaces are actually fully operational. So I'm going to go to R5. I'm going to say interface serial 020, no shutdown, interface serial 000, and I'm going to say no shutdown there. On R2, interface serial 020, no shut, and on R4, interface serial 010, no shutdown there. So what I'm expecting here is that my interfaces have changed state to up. So what I want to see is CDP neighbors, and I can see that both R2 and R4 are now up and running. So I do have the communication there. So let me now change the link between R2 and R5. So this link here, I'm now going to change it to frame relay. So the only thing that I'm going to do here and here is the encapsulation frame relay. So no other changes. So here I am on R5, encapsulation frame. Here I am on R2, encapsulation frame. So let's see what's going to happen here. So if I do show interface serial 020 now, for relatively brief period of time, I will see that interface is up and that the line protocol is up. But relatively quickly, and I need to catch it there because it is going to take about 30 seconds, 30-40 seconds before we can actually notice the change here. So let me not be too impatient. And you know, I already mentioned that I am very, very patient man for very brief periods of time. And of course, whenever I want to reproduce some failure, that takes much longer than... there we go. So here, now we can see that on R2, the interface change state to up and line protocol is down. If I go to R5, I'm going to have the same situation there, but that's not exactly what I wanted to show you. I wanted to show you one other brief situation. So let me just bring the interface down very quickly. Apologies for this. Just want to change the interface to admin down, because up down is what you usually expect, but there is one other state that is a little bit tricky to reproduce, but it's very important to be able to see it at least once so that you know what you're dealing with. Just want to see something. Okay. Okay, this one is up. Sorry for producing so much output there, but as I said, sometimes it's rather tricky to reproduce these unusual transient states. Let me see, maybe R5 already has it. No, R5 does not have it. Oh my, oh my, oh my. Let me see. I need to do a little bit more work to actually reproduce this problem, so give me just 1 second here. Oh, well, I didn't change it to frame relay. Well, that explains it. Silly me. It works much better when you actually configure it to be what you need it to be. So serial 020, what I have changed to frame relay is actually the wrong interface. I have changed the interface facing R4, not R2. So now I have changed R2 to be correct. So now I'm going to do no shutdown. And this is the state that I wanted to show you. So now you can see that the serial interface is up and line protocol is down, and it says looped. Now, I can guarantee you that this is the actual connection. R2 here is connected to R5. And you remember that when we had this as HDLC, this was no problem. We had the CDP neighbor and everything was functioning normally. But now something on R2 here is saying it's looped. Now, what is looped? This is where we have to go back to this rule here. It says that the DCE will respond to LMI inquiries by sending the LMI status, and it will never ever send an LMI inquiry. Now, R2 here, our router R2, is configured to be DT. It expects that the other side here is configured as the DCE. But in our case, because we are using the default configuration on serial 020 and the default configuration here, they are now both configured to be DTEs, which means that this router here is sending the LMI inquiries and this router here is sending LMI inquiries. But R2 here does not expect LMI inquiries back. And here is when one more thing comes into play. If I go to R5 and if I take a look at show interface serial 020, on R5, I'm going to see that the line protocol is down. So R5 is not seeing this weird looped state, but R2 here is still seeing it as looped. And here is the key. When the LMI inquiry, so this is the inquiry that is being sent, when the LMI inquiry is being sent out, there is a serial number of it. There is a sequence number that is being sent. And let's say, for the sake of simplicity, that the sequence was number 1. Now, when the interface came up on R2, if R2 was the one who sent the inquiry first, R5 here, configured as the DT, is going to receive the inquiry from a router that it doesn't expect. And what is it going to do? It's going to ignore it because it doesn't expect it. R5, on the other hand, because it's a DT, sends its own inquiry. And because interface came up first, the sequence number is also going to be 1. So now R2 is receiving an inquiry with sequence 1. And it assumes, because it is sending the same inquiry, that this is the same inquiry that for some reason was looped back. Now, this is not true. There was no loop here, but this is what R2 thinks is happening. So when you see this situation here, that you have that interface is up, line protocol is down, and it says looped, and you are using encapsulation frame relay, you basically pretty much know right away what the problem is. The problem is that on this link, no routers are configured to be frame relay switches. In other words, none of the devices are configured to be DCE devices. Now, depending on the timing, it could be one or the other. In this case, and this is why I said it might be a little bit difficult for me to reproduce, well, it turned out that the problem was that I was running encapsulation HDLC, so there was no LMI inquiry going on there. But depending on which sends this inquiry first, that will be the side that thinks is the looped one. And it's usually going to be the one that comes up last, or the one that you type no shutdown last on, because this is the one that will realize faster that the interface is up than the other side of the link. And also it helps if it's a DCE device, serial DCE, which in my case, it is. So I can see that my serial 020 here is actually DCE, and you can see here that it's a V35 connector that we are using and that the speed is 2 megabits per second. Another telltale sign is clock rate 2 megabits on the interface. You cannot enter this on a layer 1 DTE side of the connection. But as I said, these are really irrelevant. It was only the timing issue here in order to that caused R2 to have this looped in. It is because it realized that the link is up faster than the other side and it sent the LMI inquiry first. So now we are stuck in this state that R2 thinks that the interface is looped and R5 correctly assumes that the line protocol is down. Mind you, layer 1 is okay because the interface is up, we are connected, there is electricity, there are keep alives, well, not really keep alives, but there is the DCD signal, the carrier is up, so the bits are flowing back and forth, and we are actually sending some data. It is layer 2 where we have problem. Another thing that you can look at here. So if we take a look at the interface here, then this is on R2. We can see that we are sending LMI inquiries. We have sent 41 so far, and we have received 0 status responses. Here we have received 45 LMI inquiries, and we have sent 0 statuses. Now, if you are sending LMI inquiries and we are receiving them, well, that's a problem. We have the same situation on R5. Here we have 29 inquiries sent and we have received 43. So this is the problem. How do we address this problem? Well, we need to turn R5 into the frame relay switch. So let's do that next. So I'm going to again create a copy of this page. I'm going to go here, and now what we need to do is we need to configure our R5 as the frame relay switch. The configuration for that is very, very simple. So let's say just frame relay switch configuration. These are the steps. First, enable frame relay switching globally. Then create, actually there is one step between there. So step number 2 would be make interfaces frame relay DCE, then create frame relay PVC connections. Now, I call them PVCs because there are actually 2 ways to do that. One is using so-called frame routes, and the other way of doing it is using connections. I will show you both of these. So these are pretty much the same. They provide the same functionality, except that the frame routes here are part of the frame relay switching framework, and the connections are part of layer 2 VPN framework. Now, this sounds scary, I know that, but don't worry, these are actually much simpler to configure. So that's what we are going to be doing next. We are going to configure our R5 to be the frame relay switch, which means that this one here needs to be the frame relay DCE, this one needs to be the frame relay DCE, this one needs to be frame relay DTE, and this one here needs to be frame relay DTE. So let's do that very, very quickly. I'm going to start on R5, and let me bring my text editor here. I'm going to say interface serial 020, encapsulation frame relay, interface type, DCE. Really no need to bounce the interfaces, but I always found the best results are when you actually do it. And here, before everything, I'm just going to say frame relay switching. This is where I'm going to enable frame relay switching. So very, very simple configuration. So this goes on R5. So now, if I go back to R2, if I take a look at my counters, that should be happening relatively quickly. Now you can see here that we are sending LMI inquiries. So here we have sent 67, and take a look. Now we are actually receiving a status in response. Here is the second one, and take a look. We are no longer looped. Now its line protocol is down. It takes some time for this to come in. It will take three of the statuses for this to work. So there is the third status received, and we can see here in the middle of this output that the line protocol actually changed state to up, and we can see now that we have that this counter is increasing, but we are no longer receiving the frame relay inquiries. We are only receiving the statuses. On R5, show interface serial 020, oops. We are now sending the statuses, but this counter here is no longer increasing. This one stays at 54, and we can see that this one increased from 5 to 6. So now we actually have frame relay connection between R2 and R5, where R5 is acting as the switch, and we should have the same situation with R4, except on R4 we haven't configured the frame relay. So this is still HDLC, so let's configure it as frame. When we do that, we should be receiving the inquiry at some point. There it is, one inquiry has been received. And as I say, it takes some time for it to come back up, and there we go, it just came up. So now we actually have frame relay connectivity between R2 and R5 and R5 and R4. Now, we not yet have the connection between R2 and R4. What we're going to do now is we are going to make the connection between R2 and R4. So our R5 is the frame relay switch, so that doesn't change. So what we want to do is let's have a black connection between R2 and R4. So on this black connection, I want to use del C 204 on R2, and I want to use del C 402 on R4. And I want to have 192.168.24.0/24 as the IP addressing on this connection. And I will use .2 on R2, and I will use .4 on R4 as the IP address. Now, the requirements for this connection here, and I will write them down, so this is going to be the black one, is that I want to use on both sides, on R2 and R4, I want to use frame relay physical interfaces, which means I'm not going to be using any sub interfaces, and I want inverse ARP to be turned off. Now, inverse ARP is an address resolution protocol that works on frame relay. So let me just briefly give an introduction to what inverse ARP does, and we are going to see it in action as well later on, but for now I want it turned off. So let's first take a look at how ARP works, just a regular ARP. No, just basics, networking 101, the CCIE lecture for free. So what we have here is, let's say that we have host A and host B that are connected to a common switch. Now, when A wants to communicate with B, and let's say that A has an IP address for B, let's say it's 10, 10, 10, 10. So let's say that A has, for some reason, has the IP address of B in its ARP table, and it has the IP address, it knows the IP address of it, but it doesn't know what is the MAC address of B. So what A can do is it can send the broadcast here asking who has 10, 10, 10, 10. Now, the switch here being the switch, and let's say that there are some other connections on the switch, when it receives this single packet here, it's going to actually replicate and flood this broadcast out to all interfaces except the interface on which it was received, and eventually B here will receive this broadcast packet. Now, this is how ARP works, and for this to work, what we are relying on is the broadcast replication in the cloud, where our cloud here is actually just a single switch, or we might have multiple switches. Now, the reason why this works, why this is so simple, is because Ethernet is multi-access network with broadcast capability. Now, frame relay, on the other hand, is non-broadcast network, which means it's a multi-access non-broadcast network, which means we cannot do this. We cannot send a single packet to a frame relay switch and tell it, or sorry, I should say single frame to a frame relay switch and tell it, hey, send this to everyone you know about. We cannot do that. So what inverse ARP does is something very, very different. So let's here take a look at the inverse ARP. What we have here, again, let's say that we have host A, we have host B, and here let's say that we have some switch and we are connected here. So this is now frame relay switch, and let's say that we have some host C. Now on this link here, frame relay switch is going to communicate to A what are the available DLCs, and let's say that the available DLCs are the connection to C and the connection to B, and let's say that these are DLCs 102 and 103. So what A here can do is it can send out a request down DLC 102 and down DLC 103, basically saying, hi, I'm A, sorry, and ask, who are you? Now, the same question A is going to ask of B, except this is happening over another DLC. Now, one thing that I want you to take a look at is this part. Hi, I'm A. Inverse ARP is a very polite protocol. It is always going to introduce itself. Now, this hi, I'm A is actually a message, hello, this is my IP address. What is your IP address? Now, being a polite protocol, you are always going to get a response from inverse ARP. So C here will always respond back saying, oops, sorry, wrong color. It's always going to respond back saying, okay, I'm C, and B here is always going to respond with I'm B. Now, when you talk about inverse ARP, it's important to understand that we can turn off the question but you cannot turn off the answer. That means that the router, if it receives the inverse ARP request, it will always respond to it. Why? Because it's a polite route, it's a polite protocol. When you are polite, when someone says hello, you answer hello. It hurts nothing, right? Except in frame relay, it can actually hurt. Because if the lab says, make sure that you don't have any dynamic mappings in your network, basically they want you to turn off the inverse ARP, please make sure that you turn it off everywhere, because if you forget just one place, the very fact that you have received the question will create a dynamic mapping on this router here. You not only need to send the question and get the response, because when someone tells you unsolicited, hi, my name is Marco, you immediately know their name. Same thing here. Inverse ARP will learn the remote IP address if it hears the question. So when we say that inverse ARP needs to be turned off, it needs to be turned off on both sides of the connection for it to make sense. And I will demonstrate to you right now. So the first thing that we are going to do is we have already configured interfaces on R5 here to be DCE interfaces. So what we need to do is we need to configure these, oops, sorry about that. Let me just move this a little bit down. Apologies. What we need to do now is we actually need to create the delcies. So this delcy 204, I need to create it on R5 on this interface, and on this one I need to create delcy 204, and I actually need to create the cross connect between them. I need to create the PVC. So let me go to my terminal, and I'm going to start on R5. As I say, there are two ways of doing this. One is using the old frame routes that use the frame relay switching framework, and the other is slightly newer using the connect commands. I will show you both, but first let's do the traditional frame relay switching. I vaguely remember that I have enabled it, but it doesn't hurt to do it again. Let me actually do this from the text editor. So the first thing that I'm going to do is, in my text editor, I'm going to say frame route under the interface. Delcy 204 needs to go out of the interface serial 000 as Delcy 402. Now, for this to work, I actually need to create a return route on the destination interface. So basically what I need to do is these two commands. But let me first show you how it looks when you configure just one side. So now I'm going to say show frame route, and we can see here that the input interface is serial 020, interface input delcy is 204, the output interface is serial 000, and the output delcy is 402. And it says status inactive. And doesn't matter how long I actually stay here, the status will always show me inactive because it is expecting the route back. So now when I add the route back, relatively quickly, it's going to take maybe 20-30 seconds for it to start changing the status. There we go, it already changed the status. Now we can see that both of these delcies are now actually in active state. So if I go to R2, for example, if I do show frame PVC, I will see now that I have delcy 204 that is unused, so nothing is actually using this delcy, and its own interface serial 020. If I go to R4 and if I do show frame PVC, I see on serial 010, I see delcy 402. Again, it's unused, but it's active because the frame relay switch told us about it. So what I'm going to do next is, this is the configuration of R2's serial 020 interface. So what I'm going to do now is I'm going to shut this interface down, and I'm going to configure IP address 192.168.02. Actually, was it 02 that I wanted to use? Let me use 02 here instead of 24.2. So this is going to be 0. Let me correct it. Maybe I have this one here as well. Okay, that was the only place where I had it. Apologies about that. So, and I'm going to do the same thing on R4. So I'm going to say IP address, let me shut it down. IP address 192.168.04. And now on R2, I'm going to say no frame relay inverse ARP. So on R2, I'm turning off the inverse ARP. If I take a look at the configuration, this is how the interface looks on R2. And on R4, this is how interface looks there. So let me show them side by side. So this is on R4, and as you can see, I have not touched inverse ARP there, which means it's turned on. And on R2, the inverse ARP is actually turned off. Let me bring up both of those interfaces. So if I do show frame PVC, now I can see that the delcy is there. Delcy says still unused. It's going to say that for just brief time. There we go. We have this on R4. Now, let me go to R2. Okay, let's wait for some time. It actually takes about 60 seconds for this to happen. So we might need to wait just a little bit. Again, my patience kicks in. And in the meantime, I'm seeing a question, why is it so simple when you explain it? It took me some time to configure my frame relay switch at home. Well, I did answer that question before. It's always difficult when you're doing something for the first time, right? It is the practice that is going to make it appear very, very easy. And as I said, I've seen astronauts fly the space shuttle so many times. You put me behind those controls and you would have me in the news very, very quickly. The same thing here. When you're configuring something for the first time, of course it's going to be difficult. It's supposed to be difficult. We don't want anyone being a network engineer, do we? So then when you practice it, when you do it once or twice, or in my case, 81 times, it becomes a little bit easier as the time goes by. Now, this is at this moment starting to confuse me a little bit because it should have worked by now. So let me troubleshoot this a little bit. What have I done wrong? So just going to take a look at the configurations here. 192.0.2, that's okay. Show run interface serial 010. That's okay. And show frame route active. Am I getting any input packets? Okay. Now, actually, this was a telltale sign for me that it actually worked the way I expected it. We just needed to wait a little bit. Now, take a look at this. So now I'm looking at layer 3 to layer 2 map on R2. And what I'm seeing here is that IP 192.168.0.4 R4 is reachable over DLC 204, and this is a dynamically learned entry. This is inverse ARP. Now take a look, it says input packet 1. That means this doesn't tell me how many frames I received from the switch. No, this tells me how many DLCs, how many packets I received over this DLC, how many packets I received end to end. So I knew here I expected to see from R4, hello, I am R4, who are you? And by virtue of actually receiving that question, I have a dynamic entry. Now, if I go to R4 and if I do show frame map here, I'm going to see that I have a dynamic entry. So have I actually satisfied the requirements of this task? Is my inverse ARP off? No, it is not. It is actually running on this DLC, even though I was under the impression that I turned it off. So this is why I was warning you. If you are instructed to turn off the inverse ARP, you need to make sure to turn it off on all the devices that are connected to your frame relay cloud. And in this case, these are R2 and R4. So let's go and fix this problem. So on R4 now, on serial 010, I'm going to say no frame relay inverse ARP. But my problem actually persists because this dynamically learned entry is not going to be so easy to unlearn. Yeah, I'm no longer going to be asking any questions, but you know, the entries that I've learned, they stay. I have to clear them. So you can do that with clear frame in ARP. Oops, typo. So now when I do show frame map, I no longer have that mapping there. And the same thing on R2. So if I do clear frame in ARP, now I no longer have the dynamic mapping in my layer 3 to layer 2 database. So at this moment, I also do not have the communication between R2 and R4. If I cannot use the dynamic mappings, I need to use the static mappings. So let's add some static frame maps to our configuration. So what I'm going to do here is I'm going to say frame map. I want to map an IP address 192.168.0.4 to DLC 204, and on the other side, I want to do something in the opposite direction. So frame map IP 192.168.0.2.402. So now if I take a look on R2, show frame map, what I'm seeing here is that I have a static mapping. This is the the framing, end-to-end framing. It can be either Cisco or it can be IETF, but in this version of code, in this version of iOS, the difference is really academic, because the iOS will try to auto-detect what framing you're using. So even if you set something else, it doesn't really matter. Again, as I say, this used to be a big thing earlier. In earlier versions of the lab. For version 4 blueprint, this is irrelevant thing. So I'd see that this is a defined mapping and it's active. So right now from R4, I should be able to ping from R2, I should be able to ping R4, and I can see 5 exclamation marks. And as my wife says, I am the happiest when I see those exclamation marks in the lab. So if I ping from R4 to R2, I'm also getting the exclamation mark, so this is good. Now, my question to you is, and I am hoping to hear answers, so get ready to do some typing. Can I from R4 ping R4? Can I ping 192.168.04 from R4? That's very good. The overwhelming answer that I received is no. Let's just confirm that. Well, helps with do. Obviously, I cannot ping. Now, the next question is going to be crucial. Why? Why is it that I cannot ping from R4 to R4? Now, mind you, here I'm not asking you how to solve this problem. What I'm asking you is, why can I not ping? What's the reason for this ping not working? I'm smiling because the overwhelming answer that I received is exactly what I expected. You all know how to fix it. You all know that I need to add the frame mapping, and one of the answers was it's the way frame relay works. It needs to be mapped to the layer 2 to layer 3 resolution, and one was loop prevention. That's not actually it. But you have not answered my question. You are telling me how to fix it, but what's the problem? Why? I mean, it's my own IP address. Why should I not be able to ping it? If I take a look here, for example, on R4, if I do, for example, show IPsef, I will see that 192.168.04 is set to receive on serial 010. Why can I simply not ping myself? While you're thinking about that, I'm going to stop the video because I want to prepare one example there. So unrelated to this, and I just want to show you something. Totally different example. I'm going to have two routers. This is going to be R6, and this is going to be R9. This is serial 020. This is serial 020. And the network between them is 192.168.69.0/24. This is .6, this is .9, and we are running default HDLC encapsulation between them. So let me bring these two routers in. And if I take a look at the interface, show interface serial 020, on R6, I can see that this is 192.168.69.6/24. And on R9, show interface serial 020, it says 192.168.69.9/24. And we can see here that encapsulation is HDLC. So there is no frame relay involved, nothing of the sort. My question is, if I ping 192.168.69.9 from R6, will this work? Very simple. Yes, no. What do you think? Yes, of course it's going to work. Now, another question is, if I try to ping myself 192.168.69.6, will this work? Yes, no. Very good. So this works like a charm. Let's go to R9. So on R9, I'm going to ping 69.6. Will this work? What do you think? Again, yes, no. Okay, very good. And this works like a charm. Ping 192.168.69.9. Will this work? Again, simple yes, no. Oops. Help me troubleshoot this a little bit. So R6 can ping R9 and R6 can ping R6. R9 can ping R6, but R9 cannot ping R9. Again, HDLC interfaces on both sides, so no frame relay involved. where would you start troubleshooting this problem? Show run interface on R9. Well, that's of course a very logical place to start. So show run interface serial 020. That's pretty much what I have. IP address and no fair queue. So would you like to see the other side on R6? Okay. So there is the configuration of the interface on R6. Do you maybe see something that sticks out? Well, yeah, but why would an access list on R6 affect the traffic when R9 pings R9? Well, let's see what happens when R6 tries to ping R6. So obviously, I know that works. But what happens if I actually do a trace route? Now, mind you, this is my own IP address. Take a look at the trace route. It actually goes out to R9 when it gets routed back to R6. Now, when we have serial interfaces, and all serial interfaces on all Cisco routers operate in the same way, there is a serial interface, and we are perceiving it as one interface, when actually there are, and I am oversimplifying things here, there are actually two circuits. One is the transmit circuit, and the other one is the receive circuit. Now, the transmit circuit obviously sends the traffic out, and the receive circuit receives the traffic. There is no shortcut between transmit and receive inside the interface. So if we want to do self-ping, instead of sending the traffic here to interface and somehow it being returned inside the interface, what actually needs to happen is this traffic needs to go out of the interface and on the remote side either looped back or actually routed back so that we can receive it on the receive side of our circuit. Now, this has something to do with the implementation of serial interfaces on Cisco devices, nothing to do with frame relay. Now, this is what you will encounter mostly on frame relay. But there you had an example with HDLC where we had an access list on R6 preventing the ping from R9 to R9. If I do show access list here, what I'm seeing in the access list is a deny statement that denies the ICMP echo traffic from R9 to R9. So if I do a trace route from R9, so instead of just pinging, if I do trace route, I can see it going to R6 and then coming back to R9. Actually, this wasn't a very good example because trace route in iOS is not ICMP, so this will actually succeed. But we can see where this traffic goes. But if I was to change this access list just a little bit, so IP access list extended 100 node 10, and if I said deny IP this, so just deny, deny IP like this, show access list. So now I'm just going to be blocking all IP traffic, not only ICMP. So now if I do trace route, I can see it going to 69.6, and that is where the traffic is being dropped. Now, mind you, this is, as I said, a serial interface, HDLC, no frame relay involved. Now, that same exact thing is actually happening in our frame relay example. So what needs to happen here, and let me bring this in. What needs to happen here is when I try to ping from R4 to R4, what I need to do is I actually somehow need to send the traffic for 192.168.04 out of this interface, send it down this cross connect to R2, then R2 is going to route back the response, or actually route back that same traffic so that I can receive it on R4. When I'm responding to my own ping, I'm actually sending the response out of this interface where it gets routed back when it gets switched, and then it arrives back. Now, the problem here is, of course, in this part, and this is something that you have correctly identified. You all knew how to fix it. Because serial 010 is a multi-point interface, what is happening is we know where to route the packets. That's no big deal because we actually have the route. So if I do show IP route on R4, I can see that 192.168.0.0/24 is pointing out of serial interface. But let's take a look at what happens when we actually send the traffic there. So what I'm going to do here, I'm going to create a very simple access list. 100 permit ICMP any echo. So this is the only thing that I care about. And I'm going to say debug IP packet 100. Okay, so I'm going to watch for traffic that is ICMP echo traffic. And I'm going to ping 192.168.0.4 and I'm going to send only one packet. So let's see what our debug tells us. Now, the first thing that we are going to see here that the packet is actually being routed. There is no problem with that. Then we can see that we are actually generating the traffic. We are sending the packet down the encapsulation path. So we are at layer 3, we do have the route, we know where to send the traffic, and we need to send it down the layer to layer 2 so that we can actually generate the frame to send. And this is where the operation fails. We have encapsulation failed. Encapsulation failed means that we do not have layer 3 to layer 2 mapping. We know where to send the packet, that's not a big deal, the routing table tells us that. But we don't know where to send the frame. So this is why if you want to provide for self-ping in frame relay, you actually need to have a mapping. It's the combination of the serial requirements and it's the combination of the requirements that on a multi-point frame relay, you actually need to give it a delcy to send this traffic in. And it all stems from the same fact that there is no that shortcut inside the circuit where you can actually send the traffic. Now, I should clarify this. There is actually an ability to configure this shortcut, but it cannot be selective. You can configure it only for all traffic. And the command to do that is to actually enable the loopback on the interface. So here on R4, you would say interface serial 010, you would say loopback, and when you enter this, all the traffic that arrives in on transmit will actually be sent out, or the other way around. Anything that you try to send out, you will be receiving back. So it basically creates a kind of a U-loop to U-loop, kind of sends all the traffic out and everything that comes in from the inside sends back. But you cannot send the traffic out of the interface and selectively return it back. It's all or nothing. So this is actually a very bad command to configure unless you are testing something in production environments, and I am guessing that in 2013 nobody is testing anything on serial lines. It would be very, very unlikely that you are involved with that. But if you are, that is a useful command. So in order to actually fix this, and this is what all of you knew the answer for, is we need a frame relay map statement. So I'm going to go to R4, interface serial 010, and I'm going to say frame map IP 192.168.0.4, and I'm going to map it to delcy 402. So if I do show frame map, now I will have the map for the remote IP address, and I will have the map for the local IP address, which is something that I can ping. And look at how much debug output I've received. So what I'm going to do next is I'm going to send just one ping again to see what happens here. Take a look. Now here we have the output that says the traffic was routed out to the routing table. We are generating the frame. We can generate the frame, it goes out. But take a look at this. Now we have actually received the frame. So this is the source, this is the destination. We are receiving it, it's being routed. We are receiving the traffic, and we are stopping the processing of the packet. It is not going down the encapsulation process because this is packet for us. So we are now punting it up the routing engine for processing, up the routing processor. So this is really the root cause why you need that one single map statement for self-ping, and not necessarily related to frame relay, because you've seen it with the HDLC. The next thing here between R2 and R4, and mind you, let's do the same, let's apply the same fix on R2 so that R2 can ping itself. If I was to run a routing protocol between R2 and R4, let's say RIP or EIGRP or OSPF, would I be able to do that without any additional modifications? Well, I believe that we briefly mentioned it yesterday as somebody was asking me about the broadcast statement on the frame relay, and I went explaining it in the chat, so I'm now going to do it here as well. Right now, the broadcast traffic or the multicast traffic between R2 and R4 does not work, and I can easily verify that if I ping the broadcast address from R2. Take a look. This traffic is actually failing to go out. If I try it from R4, where we actually have the debug going on, so 192.168.0.255 repeat 1, I will see pretty much the same thing as I've seen before. It says, okay, this is a broadcast or multicast packet. They are from frame relay perspective treated the same way, and it says encapsulation failed. The reason for this is that the frame relay is non-broadcast media. That means it does not support broadcast traffic, which is slightly misleading statement. What frame relay does not allow me to do is it will not replicate the traffic for me. So let's say that this is a frame relay switch, and I have 2 nodes connected, let's say 3 nodes connected to it. So this is A, B, and C. What I cannot do is send a single frame to a frame relay switch and then have frame relay switch actually replicate this frame to these 2 for me. This cannot be done in frame relay. But what I can do in frame relay is I can do the replication for myself, because frame relay ultimately doesn't care what kind of traffic you are sending. So what I can do is I can send traffic to C, and I can send another copy of traffic to B. Now, frame relay switch doesn't care what's in the IP destinations of this traffic. So this could be IP multicast, or this could be IP broadcast traffic, or IPv6 multicast traffic. From frame relay's perspective, these are all unicast frames. It was a red frame that was sent to C, and it was a blue frame that was actually sent to B. Now, obviously, because I am doing the replication here, the bandwidth on this interface becomes an issue, because instead of sending just a single frame out there and have the switch fan it out, switch replicated for me, I actually have to do pseudo broadcast replication for myself. So it's not that the frame relay network does not support multicast or broadcast traffic. It does, it just won't replicate it for you. But we can send multicast or broadcast traffic. Obviously, the way to configure that, and let's do it on R4 first, would be to add the broadcast keyword on either one of these statements. So just to add to the confusion, I'm going to add it on this statement here. Now, one of the very, very common misconceptions that I have with my students is that this is an incorrect configuration. Because if we take a look, this is R4, and I'm configuring the broadcast for R4's IP address. At least that's the perception of what I've done. But this is actually not relevant, because this broadcast keyword here is the parameter of the delc and the protocol. So this command line, actually, the way it is perceived by our router is this. Oh, I cannot delete that, so let me get creative here for a second. And of course, that didn't quite work the way I wanted it to work, but I'm not giving up just yet. So basically, the way this is perceived by the router is this. The router doesn't care what the IP address is. The only thing it cares is that for IP protocol on delc 402, enable pseudo broadcast replication. Now, another thing that you might have here is instead of IP, you could have IPv6, in which case you are enabling pseudo broadcast application for IPv6. And those of you who might be going for a service provider test later on, another option that you might have here is CLNS, which is needed if you want to run ISIS over the frame relay. So this is why this IP address is irrelevant, and why this is a perfectly valid configuration here. So let's give it a test. So I'm now going to ping 192.168.0.255 repeat 1 from R4. And now what I will see is that the packet was actually sent and I have received a response. So there is the response from 192.168.02. You see that 02 actually responded to this traffic. Now, on R2, obviously, this doesn't work just yet, because on R2, I have not enabled pseudo broadcast replication. So let's go ahead and fix that on R2. Again, it doesn't matter on which entry you do that. So let's do 192. Let's try ping here. So now we should be seeing this traffic going out, and on R4, we are actually going to see some debug output because this was now echo traffic, not echo reply. Another common mistake about the broadcast statement that I see from my students is the following one. Because they're unsure about this, do I need it here, do I need it there? Sometimes just to make sure, my students do this. So now I have enabled pseudo broadcast replication on 2 of my on 2 of my frame map statements, but keep in mind that they are referring to the same delci. So let me again send just one ping. Just one ping goes out. So we can see it here that one packet was sent, and take a look at this. We have received 2 responses from R2 because this thing here is actually lying to us. One packet indeed was sent, but it doesn't tell us how many frames were sent. This one packet actually got encoded in 2 frames and were sent as basically a copy of the same traffic was sent twice to R2, and R2 responded to, from what it perceived, 2 ping packets. But we can see here that they were actually the same ping packet because it was request number 0. If I send multiple requests, what I'm going to see now is 2 packets go out, and you can see here that I'm receiving responses to request 0, and here there is an echo request or response to the request 1 that I'm receiving. So this configuration that we have now in place is something that I would highly recommend not doing. So try to avoid having broadcast statement entered twice. So this now is more correct configuration. So this is the right thing to do, not the one with 2 broadcast statements. We are going to add another link between R2 and R4, and let's call this one a red link. So we're going to add a link here, and let's make this one 214 and 412 on this side, and this will be 192.168.10/24. And for this one, so let me write down the requirements for this. We are going to use the frame relay multi-point subinterface, and we want to have inverse ARP on for this. Furthermore, for this example here, what I'm going to do is I'm not going to be using the frame routes. I'm going to use the new connect statements to get this cross connect working. So for this part here, instead of using the the frame maps, I'm going to take the delci 204 here and map it to delci 402 here and back using the connect statements, or as I like to call it, the new way of configuring frame relay switch. So let me go to the terminal, and I'm going to go to R5 here, and I will need my notepad as well. Now, for this new way of configuring frame relay connection, instead of starting in an interface configuration mode, you basically start in the global configuration mode, and all you have to do is simply say connect. And actually, let me do it in the terminal so that I can show you with the question mark. So you simply say connect, and the first thing that you need to enter here is the name of the connection. This can be anything, but I'm going to call it R2-R4-1. And the next thing that we say is let's imagine that we have side A and side B, or segment A and segment B, segment 1, segment 2, call it whatever you want to call it. So one segment will be this connection here between R2 and R5. So basically this interface on R5, and the other segment is this segment here, and that means this interface here on R5. So basically what I need here is to name that segment to specify which interface. So let's say that segment number 1 in my case here is going to be, let's say that this is segment 1, and let's say that this is segment 2 here. So what I'm going to do is I'm going to say that serial 020 and del C 214 on it are segment 1, and then I specify the segment number 2, which is going to be serial 000 and del C 412. When I press enter, I'm entering the configuration mode for this connection, and you don't need any options here. The only conceivable one that you will ever want to use here would be shutdown. Everything else applies when you are using this in combination with, for example, MPLS layer 2 VPNs or L2TP version 3, which are the topics that are not covered by the CCIE routing and switching exam. They are covered on the CCIE service provider, but since you are not studying for service provider, you don't have to worry about it. So we are basically done here. So I'm just going to press Ctrl C and exit from this configuration mode. So the only thing that I have now in the global configuration mode is this. And if I do show frame route, this command or this new connection will not show up because it's not part of the frame relay switching framework, which is what show frame route is telling me. But what I can see is if I type show connection all, I will see this connection. And you can see here that we have the identifier, we have the name. So identifier is just a random number that will get assigned sequentially, so it'd be 1, 2, 3, 4, 5, etc. Then we have the name, which is the name that we've given it. We have segment number 1 here, which is serial 020-214. We have segment 2, serial 000-412, and we can see that the state is up. Now, please keep in mind that I did have some line wrap here. These two equal signs are actually part of this long line, but I guess that someone in Cisco didn't actually count very well. So this is very wide output for unknown reasons, but this is what we have. Now, the important thing to notice here is that if I do show frame route, I have these old configs in place and I have the new one, so they can coexist. If I go to R2 and if I do show frame PVC, what I'm going to see here now are two PVCs. One is 204, the other one is 214, which is okay. This is exactly what I needed. I have created a new del C. So from R2 and R4's perspective, there is really no difference between using the old command and using the new command. It's only what happens inside the box on R5 that is slightly different. So this is, again, the new way of configuring the frame relay switch, and this basically ends my presentation on the frame relay switch itself, because these are all the commands you need to know. Frame routes, frame relay interface type DCE, you need to know how to create the frame routes, and you need to know how to create these connect statements. So that's frame relay switch. So from now on, I'm not going to be focusing too much on the frame switch. When I need a new del C, I'll just create it. But we have to continue with our task. So what I need to do here is I need to create a multi-point sub-interface on R2. So here I need to create sub-interface. I'm going to call it 1. And here I need to create sub-interface, and it needs to be multi-point on both sides. So let's do that next. So I'm going to go to R2. Actually, I'm going to first bring in my notepad. So I'm going to say interface serial 020.1 multi-point and IP address 192.168.1.2.250. So this goes to R2. On R4, what I need to do is just slightly change the IP address here, paste this in. So if I go to R2 and if I do show IP route connected, this is what I'm seeing now. I see that 192.168.10/24 is directly connected on serial 020.1. on R4, if I do show IP route connected, sorry about that, do show IP, when in doubt, slow down, do show IP route connected. So what I have here now is 192.168.10/24. So I do have the route. So if I try to ping between R2 and R4, will my ping actually work? The overwhelming answer was yes, that I should be able to ping. But let's give it a go. So I'm here on R4, and I'm going to say ping 192.168.12, and when I send the ping, I'm getting encapsulation failed. So the ping is actually failing right now. So let me turn off the debug and let's take a look at why my ping is failing. So again, I'm still on R4. I'm going to say show frame PVC. Now, this is the PVC that I actually care about, 412. Take a look. To which interface is this PVC mapped to? It's mapped to a physical interface, serial 010. So if I take a look at the running config of the interface and the sub-interface, I'm mapping the interface, the DELC 412, to this interface here. But there are no DELCs mapped to this sub-interface. So when I try to ping, I do have the route, but I don't know where to send this traffic. I don't have any DELC mapped there. So how do I bring in the DELC to my serial 010.1? And the same thing is on R2. What do I need to do to make this work? You know that I'm setting you up for a trap when I ask seemingly simple question. So again, the overwhelming answer that I received was you need to create a frame map. Well, let's read the requirements again. This needs to be a frame relay multi-point sub-interface. That's okay. But I need to have inverse ARP on. Now, the problem with inverse ARP on is that it's incompatible with frame maps. So when I use the frame map on a particular DELC, basically, I'm going to turn off inverse ARP on that DELC. I need a way to map a DELC to a sub-interface that does not involve the frame map statement. Do I have such an option? Well, as it turns out, I do have it. The option to do that is frame relay interface DELC command. Now, the problem, again, that I've seen many students struggle with is that there is this assumption that frame relay interface DELC command is somehow related to point-to-point sub-interfaces. Well, in a way, it is related to point-to-point sub-interfaces because this is where you are most likely going to see this command. But when you are running frame relay with a multi-point sub-interface, you can still use this command because the only thing that this command says is that this DELC is available on this sub-interface. And that's exactly what I need to do. I just need to tell my router R2 here that DELC 214 is actually available on a sub-interface and not on the main interface. Then what's going to kick in is the inverse ARP, which is going to help me provide my layer 3 to layer 2 resolution. So let's go and take a look at this. So I'm going to go to R2 now, and I'm going to say frame relay interface DELC 214. Now, if I do show, I'm actually going to type exit here. If I do show frame PVC now, I will see that DELC 214 is now mapped to serial 020.1. Now, on R4, show frame PVC still shows the old output. Now, I might need to wait around a minute to show you something, but it may have already happened. So what I'm going to do now is this. It actually already happened. Take a look at this. Now, you remember that in our previous task, we have actually turned off an inverse ARP on serial 010. But take a look at the highlighted entry. It's a dynamic mapping on a physical interface serial 010. Take a look at the IP address here. It's 192.168.1.2. So R4 thinks that this IP address is available on this physical interface. even though our inverse ARP is actually turned off here. How did this happen? Well, as it turns out, when you create a multi-point subinterface, which we do have on R2, so when we created this interface here, and when we actually mapped the delcy to it, inverse ARP started working on this interface. And contrary to popular belief, the inverse ARP statement configured on a physical interface is not inherited on the multi-point subinterface. So this configuration here, or I should say this configuration here, does not apply to this subinterface. So R2 is actually sending out inverse ARP requests. And remember how they look. Hello, I am R2, this is my IP address, what is your IP address? When R4 received that, it created that dynamic mapping and responded to R2, which also has a dynamic mapping, but it has actually a correct mapping because on R2, delcy214 is actually mapped to a subinterface, but on R4, it is not yet mapped. See here, delcy412 is actually mapped to a serial interface. This is yet another thing that you need to be on a lookout for with inverse ARP. You see how dangerous it can be in the lab? I mean, this can cost you to lose points. Not only that, but you are now cross-wiring the traffic. Now the traffic from a physical interface on R4 is ending up on a sub-interface on R2. Some of the traffic is ending up there. Now you can see also here that the broadcast traffic is actually mapped to this delcy, which is the default with inverse ARP, which means that if I sent, for example, OSPF hellos or EIGRP hellos or RIP updates, they would be actually arriving on R2's subinterface from a physical interface on R4. Extremely dangerous, and not to mention, it can be very annoying, because in a case of OSPF, you're going to get a log message that is going to be popping up every now and then. And I wouldn't be surprised if some of you in the labs that you are working on right now have this exact same situation, because we actually have this in a couple of our labs. So what I'm going to do now is I'm going to fix and correct this issue. Luckily, it's very easily corrected. All I have to do on R4 is actually create a subinterface, which I've already done, and say frame relay interface delcy 412. Now, with that configuration, so show frame PDC, what I've done is I have remapped the delcy from a physical interface to a subinterface, and also when I've done that, the dynamic mapping is now gone. So we now have to wait for inverse ARP to do its magic, and it's going to take around 60 seconds for it to do that unless we speed it up. And the easiest way to speed it up would be to actually bounce the interface, but we do have 60 seconds to wait. So let's give it a little wait, and if that doesn't help, we are just going to wait a little bit. And by the way, you can see now that R2 actually has an incorrect mapping, so let me just clear that, and let's wait for magic to happen. You can observe inverse, oh, it literally just happened, I believe. Oh no, not quite yet. So we need to wait a little bit, so that's okay. You can observe the inverse ARP operations. The command is debug frame events. This will actually show you the inverse ARP requests. So as they go in or go out. So maybe we can just give it a little bit of a nudge there. Sometimes sending the traffic helps. Oh no, well, I would hate to do this, but looks like it's going to be the fastest way to do it. Not enough time to wait whole day for inverse ARP to comes to its senses. So not yet there. We are seeing inactive here. We first have to wait for the switch to send us the information. There we go. Now we have the mapping, and on R4 we can actually see that this actually happened here. We got the inverse ARP, we received it, and we actually responded to it. So here I have on serial020.1, now I have the correct mapping, and I should be able to ping R4. On R4 side, let me turn off the debugs, show frame map, I should have the correct mapping for R2, and I should be able to ping it. Also, please note that when you are using inverse ARP, the pseudo broadcast is automatically turned on for you, so there is nothing you need to do to make that work. But when you are using inverse ARP, you have the problem with self-ping. This will not work. And the bad news is that when you are using inverse ARP and you are required to use only inverse ARP, there is no way to make this work. Because the way to make this work would be to configure the frame map statement. And if in the lab they tell you don't use frame map statements, well, don't use frame map statements. You just have to live with the fact that you will not be able to ping your own interface. Don't fall for the time waster that involves creating a loopback interface with an IP address and then on a multi-point interface using IP unnumbered, because this is what will happen in that case. So I'm just going to show you that example. So I'm just going to say IP unnumbered loopback 0. Take a look. It says this is available, or this is possible only on non-multi-access interfaces. So you cannot do this on a multi-point sub-interface. So let me see if this actually removed the configuration. It did not remove the IP address, which is good, so I should still be able to ping the other side. So to recap, if you are asked to use inverse ARP without the frame map statements, forget about the self-ping. That will not work, and this is something that is perfectly acceptable in the lab if this is what they actually want you to do. The question is, some of my frame interfaces that transit through frame relay switch only come up when I have no keep alive command. Now, I find that very unlikely, and here's the reason why. Because the no keep alive command, what it actually does, it turns off the LMI on the frame relay. So going back to an example that we had before, or the similar example, to a network that is similar to the example that we had before. So I'm going to reuse R6 and R9. You may remember them from the HDLC self-ping example before. So what I've done is I have removed that one access list that was preventing the traffic, and I have also removed all the configurations from the interfaces interconnecting R6 and R9. So here we have 020 interfaces. So let's say that I wanted to have between R6 and R9, I wanted to have two logical connections. I wanted to have a blue DELC and a red DELC. So let's say that this is going to be 609 on this side and 609 on this side, and that the red one is going to be 906 and 906, and that I want to run, let's say, 192.168.96.0/24 here, and that I wanted to run 192.168.69.0/24 here. Again, 6, 9 on two other sides. So I have one interface and I want to have two logical connections between these two devices. Now, there are two ways I can solve this, but let's just blindly go ahead and configure this. So what I'm going to do now is I'm going to configure interface serial020 on both sides to be frame relay, and I'm going to create a sub interface here. So let's say that this is going to be 69 interface, point-to-point type, IP address 192.168.69.6. Just correct the typo that I had there. And the other one is going to be 96, like so. And let's map the DELC. So frame relay interface DELC 609 here, and DELC 906 here. And finally, let's do no shutdown. So this would be the configuration on R6, and on R9, basically what I need to change is this to 9. So if I go to R9 and paste this in, what's going to happen here is the interface is going to change state to down, it's going to change state to up. But if I do show interface serial020, here, remember this? It's going to show up as looped. Why is it showing up as looped? Because we are sending the inquiries and we are receiving the inquiries. On R9 here, we are seeing up and down. So I don't have the frame relay switch here. This is something that is called back-to-back frame relay. Now, when you have this configuration here, this is where we basically, on this interface here and on this interface here, we need to do no keep alive. Now, when we do this no keep alive here, basically what we are going to say is we are turning off the LMI. So there will be no inquiries, therefore there will be no loop. So this is one solution for this. Another one would be to declare one of these interfaces as the DCE, even though we don't have the frame relay switch. So if I go back to my configuration here, so actually I need the text editor, so let me bring it up. So what I'm going to do here is I'm just going to say no keep alive. That's the only change. So this goes to R9, this goes to R6. So now if I do show interface serial 020, when the interface actually comes up, I will see here, you see it says encapsulation frame relay, loopback not set, keep alive not set, which means we are not sending any LMI inquiries. And you see, remember that old status about the LMI inquiries, sent LMI inquiries received, the statuses, that's all gone. Because right now, we are not actually using any LMI. If I do show IP route, I'm going to see those two routes, and I can, in fact, ping the other side. So if I do ping 69.9, I can ping the other side, and if I try to ping 96.9, I can ping the other side. So this is where these are the most common situations when you would have to enable no keep alive. But mind you, one more thing. There is actually a situation that is similar to what you describe, and that is that sometimes when you're going to the frame relay switch, you need to do it. So let's say here that you had a frame relay switch. So this is a frame relay switch, and you have router R1 and you have router R2. Now, if you have mistakenly configured this interface here as the frame relay DCE using frame relay interface type DCE command, in that case, you would actually have to turn off the keep alives. Why? Because you are sending the status here, and you are never ever going to send the inquiry, which means that this guy here will never receive an inquiry from you, and it will bring the interface down. You, on the other hand, are expecting to receive the inquiry from the frame relay switch, which you will never receive. Therefore, you are going to bring your interface down. So if for whatever reason you have mistakenly configured this as the frame relay DCE, in that case, you need to configure no keep alive. Another situation in which you may run in is if on this side here, you are using, let's say, Cisco as the LMI type, and on this side, you for whatever reason decide to use ANSI, there is going to be a discrepancy here, which again is going to cause the interface to go down on this side. If you use no keep alive on both sides of this connection, the frame relay switch and on your router, you're going to maintain the appearance of this connection being up, when in fact it's semi-up, because you will not have situation, the frame relay switch cannot now communicate which DLCs are actually active on your connection. It might have some active DLCs, but it cannot tell you that because you are turning off the LMI. These are the two examples that we went through so far. So we have built the black DLC between R2 and R4, and we have built the red DLC. Let's add green DLC here. And this green DLC here is going to be 2 to 4. Oops, sorry about that. It is going to be 2 to 4 on this side, and it's going to be 4 to 2 on this side. The IP addressing scheme is going to be 192.168.2.0/24. And here are the requirements, and this is going to be very, very, very easy, straightforward. We are going to use frame relay point-to-point subinterface. and there is no inverse ARP to worry about. When you are using a point-to-point sub-interfaces, there is no inverse ARP. So let's start this configuration by going to our R5. Actually, let me bring my R5. There it is. So going to R5, and where we have that connect statement. So this is pretty much the same thing I have to do. So I'm just going to paste it in. This is going to be R2, R4, connection number 2, 2 to 4, going to 4 to 2, just confirming that it actually got created. There it is. And on R2, what I should be seeing, show frame relay PVC. Okay, not just yet. I was a little bit faster than iOS. There we go. Delci 2 to 4 is now available, but keep in mind, it is available on serial 020 by default, so I have to move it to a sub interface. So let's do that. I'm going to go to interface serial 020, going to create a sub interface number 2, going to say point to point, I'm going to say IP address 192.168.2.2, and then I'm going to say frame relay interface type, interface Delci 2 to 4. And this is going to be the error message that is going to meet me now. It says that PVC is already assigned to interface serial 020. In this version of iOS, in the version of iOS that you will have in the lab, this is an annoying situation that you will encounter. When you are creating a point-to-point sub-interface, for a Delci that is already mapped to a physical interface, there will be this error message. There are multiple ways of actually solving this. Some are more intrusive than the others, but one that I found works the best is to actually go to a physical interface and do no frame relay interface Delci 2 to 4. So on a physical interface, I'm telling the router, delete this Delci from the interface. So now if I do show frame relay PVC, I will see, okay, sorry about that. I will see that this interface is actually gone from the mapping. But there is a problem with that. That is that this command that I just entered is not actually in the running configuration. It does take effect, so Delci was actually removed, but you've seen here on the output that I did just prior to the one that I said was okay, that Delci was present. Now, the reason why it was present is that every, 3 or 4 LMI inquiries, the router is going to request a full status update. When that happens, the router is going to relearn the Delci that you just removed. So unless you have already mapped it to a sub-interface in the meantime, after some period of time, that Delci, oops, I just removed it. I was hoping that, that I would be able to show you this. Oh, there it is, actually, it just showed up. I was very lucky. So here the Delci showed up, even though I have actually removed it from the interface. So you might be unlucky that you type in this command, so now it's removed from interface, then you go to a sub-interface, and then when you type frame relay interface Delci, or actually I can just do it like this, you get that error message again. Well, despair not, just remove it from the interface and do it again. Or even better, just do this in one single copy-paste action. So you just go to interface serial 020, say no frame interface Delci 2 to 4, then go to the sub-interface mode and create it. So you take this, copy paste, and if you get the error message, you know that PVC is present, you just paste this couple of times. Now, if you're trying to delete the Delci that doesn't exist, the router will complain, but do you really care about the router complaining? I don't. So let's do the same thing on R4. So there, this is interface 1, and this is Delci 422, and we need an IP address. So we're going to R4. So here we're going to, oops, Going to paste this in. We got no error messages there, so show frame PVC. What I'm looking for is 4:2 mapped to a subinterface, which it is, and on R2 here, show frame PVC. On R2, I'm looking that delc 224 is mapped to a subinterface, which it is. Show IP route connected shows me that this subnet is pointing to a subinterface, so I should be able to ping R4. I should also be able to ping myself. Now, the reason why I can ping myself with no additional action is if I take a look at the show frame map. Now, for this delc here, you see that no actual IP addresses are mapped to a delc. It just says this is a point-to-point delc. Now, so let me take a look at the configuration of the interface here. When we declare a subinterface as point-to-point, we are telling the router you are going to have one and only one delc available on this subinterface. Now, subinterfaces are perceived by upper layer protocols as individual interfaces, which means no matter which traffic I need to send out of this interface, there is only one way out, and this is this interface. Is it going to be a ping to a remote site? Is it going to be ping to my own IP address, or is it going to be broadcast traffic? It doesn't matter, it all goes out because this is a point-to-point delc. Point-to-point delcs are by far the easiest configuration that you may encounter in the CCIE lab because they behave in a way in just exactly the same way as point-to-point interfaces do, like PPP or HDLC. Now, usual warning is that if something looks to be very, very simple technology-wise, it's unlikely to be encountered in the lab. For point-to-point subinterfaces, the situation is the exact opposite. In these days, in the lab, point-to-point interfaces are most likely to be seen in the lab. Everything else you need to be on a lookout for, you need to be aware of it, but it is not very likely to be encountered in the lab. So basically, past hour and a half, I have wasted your time. Not really. You still need to be on a lookout for it. It could be in the troubleshooting question. It could still be in the configuration section. You could be asked to configure it. Let's build blue delc. And the blue delc, again, is going to be between R2 and R4. So it's going to be again, I make the same mistake. So it's going to be 2, 3, 4 on this side, and 4, 3, 2 on this side. And the IP addressing is 192.168.3.0/24. Now, this is going to be a little bit trickier. So on this side, I'm going to have slightly different setup on R2 and R4. So on R2 side, I want to use point-to-point subinterface, and on this side, I want to use multi-point subinterface. Now, I want R2 to authenticate R4 using MSCHAP version 2, and I want R4, I want R4 to authenticate R2 using EAP. So, what do I need to do here? Does Frame Relay support any authentication by default? There is no authentication in Frame Relay, and if you want to do authentication in Frame Relay, we actually have to run PPP over Frame Relay. And then anything that PPP supports, Frame Relay will support. So let's start by building this PVC between R2 and R4. So I'm going to go to my R5, going to create the new connection. Again, very, very simple stuff. There we go. I'm just going to confirm it exists, and then I'm going to prepare the configurations that I'm going to be needing here. So I'm going to start with R2 side. So interface serial 020. I'm going to say no frame relay interface delc 2, 3, 4. Then I need to create subinterface, and my memory gives me up here. Do I need point-to-point subinterface? Yes, it's point-to-point. So this is going to be interface.3 point-to-point. And here I'm going to say frame relay interface delc234 PPP, and here I have to specify, I'm going to need a little bit more space. I'm going to specify the virtual template to use. So let's just use virtual template 24. Okay? That's it. I don't have to configure anything else on the sub interface. Now I have to configure the virtual template itself. So virtual template 24. Again, remember what I told you earlier. I know the encapsulation is PPP by default, but I'm not going to trust iOS about it. I'm going to set it. It takes me exactly 0.25 of a second to do that, 250 milliseconds. So the next thing that I have to do is see who is authenticating who. R2 needs to authenticate R4 using MSCHAP version 2. So what I need to do here is really first create the username for R4. I'm just going to use R4 as the username and password IP expert, and I'm going to say PPP authentication MSCHAP version 2. Now I also know that R4 will be asking for my credentials using EAP. So let's give it that answer. So I'm going to say PPP identity R2 PPP EAP identity and PPP EAP password IP expert. So this is the configuration on R2. Now this is going to be the configuration on R4. I'm going to put them one above the other, just so you can, let me see if I can fit them both somehow. Probably can. There we go, this will work. So I'm going to paste this in. Now the configuration on R4, I'm expecting the username from R2. This changes, this changes, this changes, this changes to multipoint. This changes. Actually, what I'm missing here is an IP address. So let's add the IP addresses here. And here I'm expecting EAP, and I need to respond with CHAP. Now the problem is when you are using EAP as authentication and consistency of iOS, there are 10 commandments of iOS. Commandment number 1, thou shalt not be consistent. And these were the 10 commandments of iOS. So when you are using EAP as the authentication, you are expected to use Radius. If you're not using Radius and you actually want to use the local database, which is what we want to do, you actually need to tell the router to use local database. So we need to tell it PPP EAP local. So let's start with R2's configuration. Let me switch to R2. So this is the configuration on R2, and on R4, this will be the configuration. So I'm going to paste it in. And when I'm done with that, I should be seeing that interface virtual access has changed state to up. So if I do show IP route connected, take a look. Just like with regular PPP, I do have two routes in the routing table. One is /24, which I configured, and the other one is the IP address for the neighbor. I can ping the neighbor, but I cannot ping myself. Absolutely the same situation is on R2 right now. So if I do show IP route connected, I can ping 4, but I cannot ping my own IP address. If you want to provide for self-ping in this scenario here, what we would need to do is create a loopback interface, and then on this interface virtual template, instead of setting the IP address, we would say IP unnumbered that loopback interface. So I'm going to do that just on R4, just for fun. So I'm going to say interface virtual template 24 IP unnumbered loopback 4, and then I'm going to create interface loopback 4, and I'm going to say IP address like so. So if I do show IP route connected, now this is what I'm seeing. And this is where that /32 route may start making some sense. Take a look at this. Now, my /24 is reachable through the loopback. Now, if this was the only route that I actually had in my routing table, I would never be able to ping R2 from R4. Why? Because I would be sending traffic out of the loopback interface. But now, when PPP over frame relay is actually up and running, and when I learned /32 route from the neighbor, I know that that particular host is actually reachable through that virtual access interface and not through my loopback. So at this point, I can ping my neighbor from R4, but I can also ping myself, because this traffic here is going out of the frame relay interface, right? It's actually going through the virtual access interface, which is then going over the frame relay and reaches R2, but this traffic is actually going out of the loopback interface. So I have two different destinations for this traffic. So this is one of the reasons why we have that /32 route, the one that I talked about when I talked about PPP itself. So as far as I'm concerned, this is as complicated as frame relay can get in the lab. Now, of course, there are more topics that are related to frame relay, like QoS configuration on the frame relay and interaction of frame relay with routing protocols. But these are the topics that I'm going to cover when I talk about the QoS and when I talk about those individual routing protocols.